Hello and welcome to the Chapter 5 podcast on Section 5.6. Today we're going to be discussing Hess's Law. Hess's Law basically states this, that the enthalpy for a reaction is always the same whether it takes place in one single reaction step or whether it takes place in a series of reaction steps. Since enthalpy is a state function, the number of steps doesn't really matter. So we're able to calculate energy changes for things that are difficult to directly measure. Sometimes if we want to know the change in enthalpy for a reaction, what we can do is we can combine other reactions where we know the enthalpies to be able to figure out the actual enthalpy of the reaction. So for instance here, for this particular example, if I want to know the overall reaction that's on the bottom, we could add two other smaller equations together and then get our enthalpy change. Okay, so there's a way to go from what you see here to what you see here. Adding equations, I don't know if you've done this before, but if you haven't, it's like adding mathematical equations, like back in algebra and math analysis. Instead of lining up the equal sign, what we do is we line up the arrow, and so reactants on the left-hand side get added together, and products on the right-hand side get added together, and then the delta H's would also be added together as well. Okay, and then there's a negative for this that's missing, and we'll talk a little bit more about this in a moment because there's some rules and things you have to be aware of. So the rules for Hess's Law. What you can do to any equation, if you need to in order to get the final answer, is you can reverse reactions. So in other words, I can take this arrow here and I can reverse it. Oh, this is messed up. So for instance, so I have the reaction in this way, and you see how it's negative. This is supposed to be an equal sign. So pretend that's equals. And when I reverse the arrow, what ends up happening is the sign of the delta H also reverses. So if it's negative in one direction, if I reverse the arrow, then the sign reverses also. So if it's negative in one direction, it's positive in the opposite direction. Also, what you can do is, in order to make sure things are eliminated that you don't want in your overall reaction, you can multiply equations by whole number factors. But when you do that, you have to multiply the delta H by that same factor. So let's say we multiply this whole reaction here. I'm missing parentheses. Boy, I really messed this one up. If I multiply this whole reaction here by 2, you'll notice that the 2 gets multiplied into every coefficient. And then when I do that, that actually doubles the value of the enthalpy. Okay. When you get your overall reaction, there are substances that don't show up in the overall reaction, have to cancel out. So the net equation must exactly, underline for emphasis, match the desired equation. Okay, so notice how things will get eliminated if they appear on both sides of the arrow. So it's kind of like similar to eliminating spectator ions, like when we did net ionic equations. Okay, and then we line up the arrow and then we add them up. Okay. Alrighty. So here's a sample Hess's Law calculation. Let's say this is the overall reaction I want to know the enthalpy change for, and these three reactions here are what I have to work with. Okay, so part of what you're going to have to do is you're going to have to figure out how to add these up. Also, don't be freaked out by fractions that show up in these as these coefficients, because this is something that comes up all the time, and it makes it easier to visualize if it's reduced like this. So the way you do this is you want to look at the overall reaction. That'll give you an inkling in terms of where things need to be. In other words, is this okay, or do I have to reverse it, or things like that. We look at this reaction, and you notice that we want NO and NO2 on the left and right hand side respectively. So this first reaction we can leave as is. In other words, we don't have to reverse the arrow. But notice that there are some undesirable things like this that don't show up in this overall reaction, that show up in this reaction, that we have to get rid of. So we're going to have to figure out how to eliminate O2 and the ozone. we can use these other reactions in order to help us do that. So when we look at the next reaction, notice how we have to reverse this reaction here. So we're flipping the arrow so that way we can cancel out O2s. And so when we do that, we not only need to flip the arrow, we're also going to have to multiply it by a factor because we don't want fractions of O2. We need to eliminate the whole thing. So we not only flip the arrow, we also multiply this reaction by 2. So notice how the delta H gets doubled, but also the sign changes to positive because we reverse the reaction. To help us, we also know that we need O on the left-hand side. So this third reaction is going to provide us with our second reactant. And we can see here that this reaction is going to need to be reversed. So we reverse it. And so the 495 now becomes negative, and now hopefully things will line up in terms of equaling up our overall reaction. So when we multiply, the reason why we have to multiply this by 2 is we have to make sure that everything cancels out here. Okay, if we don't multiply this by 2, then it isn't really possible. When we add these things up, you'll notice that the O3s get eliminated as well as the O2s. Okay, leaving us with our overall reaction. However, everything's double of what it should be. So we have to reduce this into lowest terms, so we divide everything by 2. And remember, when we do that, we also have to divide the enthalpy by 2. So the bottom answer is our final answer. Again, this seems pretty difficult, but after you do a few of these, they get really easy. And we'll do some in class. And until next time.